As you all know, this is an open forum for information and collaboration about kelp research and monitoring. So the whole goal here is to share information. And that you will be given no work plans, you will be given no homework. And for many of us, that's a wonderful thing. It's facilitated by myself, Helen Berry, and Bree Turner. And to join or leave this list, just email us. And anyone can join. This is a low barrier work group. And then finally, I'd like to mention two things, which is our next meeting was scheduled for October 16th, but that is the date of the South Sound Science Symposium. So we're proposing it to make it 1 week later, which is October 23rd. And if any of you know of any big conflicts on that date, let us know. Otherwise, we'll officially change the meeting next week. And then finally, at the next meeting in October, we'll also have a quick discussion about any potential changes to this work group. So if you have recommendations, what you'd like to see change, anything, let us know. And we did that last about 2 years ago. And so we want to check in again. And then finally now in the chat, if you could please introduce yourself and provide any updates and request topics, that's a great way for people to start talking amongst themselves. And that's the main goal here, is for people to connect and to create linkages among all this great work. So today is a really fun agenda. We'll get 5-minute announcements from 3 folks, Jason, Toft, Danielle, and Gray. And then we have 1, 2, 3, 4, 5 20-minute talks where we're going to get into detail on either ongoing projects or recent reports, and we'll give you a summary of those. And as I think you all know, we are recording this meeting, and we will post the recording on the website because there are a lot of people who can't make it to the meeting and they love to go back and watch the recording. So on that note, I'll ask Bree, is there anything else we need to mention before we move to presentations?
I think you covered it.
Okay, great. I will stop sharing, and I'll also put the PDF of the agenda in the chat, and we'll pass it to Jason for the first about 5-minute update.
Awesome. Thanks, Helen. Let me start sharing here. Okay, great to see everyone. And I'm excited to kick this off for 5 minutes. So I will talk to you for 5 minutes about fish use of bull kelp in Puget Sound and our plan for our summer fieldwork. And why are we doing this, you may ask. And one of the reasons, big reasons, is over the past 20 years, we in the wet lab here at UW have done a bunch of snorkel surveys, but always for other reasons besides bull kelp. It's always been to assess effectiveness of shoreline restoration or impacts of infrastructure. But you can see here, oftentimes when we're out, there's bull kelp kind of around. And we're always doing these to look for juvenile salmon and forage fish, are 2 of the main groups that we're trying to find information on. So luckily for us, we received some state legislative funding. And as part of that, we are planning to snorkel at a bunch of sites, mostly in Puget Sound. And this is to build off of the good work that Ann Schaefer and CWI have done in the Straits at Freshwater and Crescent Bays. And again, the main reason for this is there's just a huge data gap. You know, you often see in management plans that bull kelp has great functions for, say, juvenile salmon and forage fish. That very well may be the case, but there's basically no data in most of Puget Sound. And this is areas where they're closer to major deltas that are having juvenile salmon outmigrate from. So we wanted to fill this data gap. Okay, where are we doing this? Here's a map based on the indicator for bull kelp extent, floating kelp extent. And all of the stars are places where we're planning to snorkel this summer. We want to build off of the perimeter surveys so we can have area of bull kelp beds in our analysis. And as you can see, all of the yellow stars, you know, up to Cherry Point and down to hopefully Squaxin. We want to get a really good spatial extent. There's 19 stars here. Ourselves at UW will be going out, and we're partnering with anyone who wants to partner with us You'll notice some stars on Vashon Maury Islands. And so the Vashon Nature Center, Bianca and Taylor and others out there will snorkel around there, and we'll meet up to overlap for protocols and all that. So there's 13 main sites. We'll be out at UW, and then Vashon Nature Center 3. And then there's 3 I put here as likely. We're planning to go to them. We thought it'd be neat to tie into Anne's work at Crescent and Freshwater Bays so we can connect the main Puget Sound area to the Straits. And then we're planning to go to Squaxin. It's just the one site that requires boat access. So we just have a little bit more work to do to plan that one. So we're trying to get really good spatial cover, hopefully up to 19 sites. But that means we're going out to each of these beds once this summer. And so we wanted to have good temporal replication as well. So we're going to pick either Magnolia or Lincoln Park, the 2 beds closest to UW, and get out there at least 10 times this summer is the plan. So we can have one local site where we get temporal replication. There's a lot going on at a bunch of these sites. So if you see a star that you're really into and want to send along info or partner with us, that's great. If you're having heartburn that your favorite bull kelp bed is not on this, let me know. We can always try to do more, and especially if there's other people to work with. So what are we doing for our protocols? I'm going to show you our plan, and it's always fascinating clicking around. I love the indicator map. It's so much fun to click around, and when you do it, I start to notice all the different sizes and shapes of all these different beds. And so we've worked a bunch talking with others and trying to come up with a protocol that we think will work at a bunch of different beds, shapes, and sizes. And this is the one at Magnolia. And here's our plan. And so we wanted to do snorkel surveys. Again, this is at the surface. We're looking for fish that are not being surveyed, say, by the reef check surveys that are more demersal fish. We're looking up in the bull kelp bed. And we wanted to hit the shallow and the deep edges of the bull kelp bed and in the middle, and then just partner that with some open water transects. So we can more or less replicate the water depths, distance from shore, all that kind of stuff, and have a good comparison so we know how fish are using the bull kelp beds compared to open water. We've come around to focusing on, well, low tides, meaning mostly low currents, so we can get out there and not be pushed all over the place. 50-meter transects is what we're going for. We're going to standardize them by visibility, not by like Reef Check does or others with a 2-meter width, where we have a Secchi disc with us. So if there's really great visibility and we can see farther, we want to count all the fish we can see. We'll have 2 snorkelers in the water and then 1 kayaker. The kayaker will be out there for safety and whatnot, but also to do things like look at bull kelp density. And that will be in a 2-meter swath. And then the last bullet is just varying different ways that we're planning to measure transect length. We'll get out the first week in June and test a lot of this and get our protocols down. So my last slide is just showing you quickly our summer field schedule. I'm going to put in the chat a link. This is a Google spreadsheet. And what I would love is you see column C here. It says partner scheduling notes. There's a lot going on. If you have anything you want to note about any of these sites, please do. You know, there's reasons for us not to be out there on the same day as, say, kayakers or scuba divers, so we're not disturbing fish. But then, of course, there's reasons to build together and have data overlap. So any kind of notes you want to put in that column C, please do. And when I'm done speaking, I'll just pop that into the chat. Alrighty, thank you.
Thank you so much. We unfortunately don't have time for questions, but again, if you do have a question, feel free to put your question in the chat for Jason, and hopefully he can follow up with that. Next up is Danielle with DNR, and you have some announcements here for us.
Yes. Can you see my slide and hear me?
Yes, looks great.
Perfect.
Sounds great.
So I'll do a few quick updates on what we've been working on. First, some of you may have seen this, but if you haven't, we've released an ArcGIS story map with our fixed wing aerial monitoring data from 2022. And this is our 4-band 6-inch resolution imagery that we collected at low tide and flat current conditions across about 760,000 acres in Washington. And so this covers a lot of area where there are bull kelp and giant kelp beds in the state, and complements our other work and work of our partners in other areas of the state. The story map has a little bit of information for folks who maybe aren't as familiar with how fixed wing imaging works, including showing how we use the near infrared green and blue bands to make the kelp canopy pop. And then it also includes an interactive map with some points that we've chosen for folks to explore, but you can also zoom in and explore around wherever you want to in this location. And we will be we collected more imagery last year for most of the same area that we have in this map. And we're working on figuring out our contract for this year as well. So we're trying to really build up our understanding of floating kelp canopies at a pretty fine resolution across the state. For those of you who might want to use these data, we have the imagery available as a hosted image service online. And we have some information about how to add it to an ArcGIS Online map or to ArcGIS Pro. If you have troubles with that or you want a specific area, like a subset imagery, and you're not able to use these, please just let me know. I'm happy to share and get folks linked up with that. Our little sneak peek is our next step. We're working on our image classification, and here's a little example of that. We are currently running all of that for the 2022 imagery, and we will end up with extent across the entire survey area. We've also updated the Floating Kelp Indicator, which is updated through the data in 2022. There were some minor changes to long-term trends at a few locations, but there weren't any changes to subbasin status. We added 2 new MRC sites, which reached the threshold for inclusion in the indicator, and we're continuing to work on adding more sites as we move forward. And looking forward, like I said, we're working on projects and proposals to increase the baseline data, especially for these areas of insufficient data. One of the proposals that we're really excited about right now is working on looking at 30 years of change in the northeastern Puget Sound, using some imagery from 95 and 96. As well as the imagery I just showed. Stay tuned for that. And then next, yep. Okay, sorry folks. And next, we're looking at historical change in bull kelp near Seattle, and I'll hand over to Gray.
Thank you so much. Please put any questions in the chat.
Yeah, and I will pick it right up from Danielle and talk a little bit about a project I've been working on with a small subset of some historic images from the 80s of the Seattle waterfront. And I'm going to fly through this story map, so don't be freaked out when I like rapidly scroll past text, because I'll link out the story map later for folks who want to dig into it a little bit more. And this project's ongoing, so everything is still preliminary, but essentially, we're looking at these aerial photographs from 1984 that Ron Tom collected that were in 35mm slide format, and we got them scanned in at a high resolution. And you can see a couple of things right away. One, there is floating kelp visible in these images. They were originally collected as part of a baseline study for finding the best location for a wastewater treatment outfall. So you can see some vegetation in them, which is cool. If they are a little degraded, or there's some big light leaks and faded areas, so it's a little complicated. And then the other main thing of note here is that this imagery is really oblique. So that just means it's at an angle that's lower than directly overhead. And that creates some challenges for mapping. And that's really obvious in this photo of Pier 91 here in Smith Cove. And here's a little diagram of how the pixels change when your camera angle changes relative to our like direct overhead imagery that we're used to working with remote sensing. However, despite those challenges, we still can get some spatial data from this data set. And so what I've done here is just used the major visible shoreline features, like big boulders and rocks. And like, this is a great example of the Fauntleroy ferry terminal and use those to line these images up along shore. This isn't the same thing as like an ortho image, so they're not accurate to the ground, but they do give us some spatial context to evaluate the imagery. So we went through and identified where there was floating kelp present in these photographs, and here's an example of that. And then using this classification scheme that Helen created for mapping the linear extent of kelp in central Puget Sound in 2019, we broke it down beyond just presence absence to describe a little bit more about the like density and abundance of plants. And it was not just me reviewing these photographs. 9 other staff at Nearshore helped me review these. Thank you for your time and generosity and knowledge. And also a lot of folks went through and reviewed these images because, as I mentioned, they are a little grainy and it's a little hard to tell what's going on. So to help increase our confidence in our descriptions of what is happening here, I had a bunch of folks go through and respond for each slide what they think is happening. And then with those responses and with those big visible shoreline features like boulders and stuff, I was able to segment the -6 meter mean low shoreline contour and describe kelp presence along that. So this orange area is showing kelp presence here. And I have put my little image mosaic things on a map here that you can click around in the story map if you're interested. And so here's these photographs of this kelp forest at Magnolia, which I know a lot of folks work at that site, wrapping around Elliott Bay. And I'll jump quickly into our preliminary results for these couple of areas. This orange is showing us where the photo footprints are. So we've got this Magnolia area, some segments of the West Seattle shoreline, and this part of the Fauntleroy Cove, which is unfortunately right below where the current Lincoln bed site is, that current bed that lots of folks work at. So that's a bummer, but preliminary mapping results, we see that in 1984, that nice wide kelp forest that lots of folks are familiar with at Magnolia used to wrap all the way into Smith Cove. And now with the construction of Elliott Bay Marina, which was, they started building that in 89, we see that kelp bed is sort of shrunk a little bit, and Julia is going to talk a lot more about more data sources than just this boat-based map that I'm comparing to here. And then in West Seattle, there's not a lot to remark on here other than there was a lot of kelp that we are pretty confident was present along the shoreline in 1984 that does not appear in the 2019 synoptic survey results. And again, unfortunate that it's right below where that current bed is, so we don't know what's going on there in 1984, but some more data about where kelp has changed over time. And the key takeaways are things that I have already said, so apologies for this big block of text. We're working on ways to quantify bed area from this data set, so hopefully we can get a little bit more information about quantifying that change over time. And if folks have thoughts or comments or questions, please reach out. And yeah, and thanks to Ron and Tom for giving us this excellent data set to work with.
Thank you. And thanks to all of the folks who let out on the announcements. Really interesting projects. And hopefully there's some good connections being made already across this community. We are now gonna transition into our longer presentations. As Helen noted earlier, we have several 20-minute presentations, and I'll leave it up to the presenters how much of that 20 minutes you want to allow to presentation versus question and answer, but I will give you at least a 3-minute warning before the end of those 20 minutes. Hi, Jesse, I see you there. With your video on, you're the first one up with PSRF. Welcome.
Great.
Take it away.
You got it. Thank you so much. Yeah, I should be keeping it to 15 minutes and then some time for questions, but do give me a 3-minute warning if you're pulling me off the stage. All right. So exciting to be able to follow after Gray. It's so cool to hear all the work that DNR is doing and all of the cool work that's going to be going down this summer, people we're working with and people that we're excited to continue to work with. So let me get this up and going. Is everyone seeing this all right? Looking good? Great. Awesome. Thank you. Well, good morning, everyone. As Bree so kindly introduced me, my name is Jessie Florendo, and I am the program coordinator at the Habitat team at Puget Sound Restoration Fund. It's so exciting to engage you all in this open forum of knowledge sharing, as Helen mentioned, because I have the exciting opportunity to walk you all through our team's kelp lab, which is shedding light both on the space itself, which is a bit of a mystery that folks at the hatchery like to remind us of that, as well as the enhanced capacity that our team has to respond to bull kelp decline across the region due to our kelp lab. This presentation will cover how our team is able to collect and preserve wild material, how we can control and promote the growth of that microscopic life stage, and what are some implications and future improvements for this work for restoration in general. All right, our lab, pictured here, small but mighty, is sited at the NOAA Fisheries Research Station in Manchester, Washington, which is co-sited with the PSRF Ken Chu Center hatchery. While our team has been doing Olympia oyster and pinto abalone work on this site for years, the kelp lab is a newer addition to that scope of work and is dedicated to native kelp species. Currently, with an emphasis on the native canopy-forming species bull kelp, or Nereocystis leuciana. Although it was constructed and available earlier, because of COVID restrictions in 2020, our team wasn't able to get full access in this space until the first half of 2022, meaning that we're now coming into our second summer in this space. Generally, this lab suits Puget Sound Restoration Fund's mission of restoring significant native species in the southern Salish Sea, who play a myriad of diverse and important roles like creating habitat, cycling nutrients, improving water quality, and so much more. While our team works on monitoring the bull kelp population across Puget Sound and the Strait of Juan de Fuca in partnership with regulators, tribes, and community members, this lab builds a different capacity. It provides us with the ability to grow and preserve genetic material from disparate kelp beds, which are then securely protected within the lab, as well as being accessible year-round. This access is important for both our own needs and projects, like our annual kelp bed enhancement at Jefferson Head, as well as being available for research partners and additional studies, which can enable us to improve our understanding of the gametophyte, or that microscopic life stage, as well as understanding that can better inform future restoration action in general. All the hard work in this lab starts very soon from now, actually, waiting for when the bull kelp matures and reaches the surface, which is around June, depending on where in Washington a kelp bed may be. When the blades reach the surface and grow rapidly, they begin to produce those darkened patches of source, like the one pictured here, which in the wild would naturally fall out of the blade and release spores into the water column. Our team is able to collect a number of those source patches from a wild kelp bed and induce them to release spores in our lab, a process called sporulation, which includes the mechanical cleaning and desiccation of the source segment. Each year, our team aims to add 2 to 4 new sites to our collection through this process, with an emphasis on geographic locations where we lack representative populations, as well as currently an emphasis on Nereocystis. We're beginning to investigate and experiment with other kelp species at this time, a project which began last year and that we're hoping to build on this year. Our protocol for sporulation was developed under the guidance of the Philippe Alberto Lab at the University of Wisconsin, who remains an ongoing collaborator and guide for all of our projects. After that initial sporulation process, our team will culture the spores as they begin to grow puffy, like pom-poms, as we call them, and become increasingly visible to the naked eye. Staff monitor them weekly, checking in on the density of gametophytes in a single petri dish, as well as how the individual gametophytes are developing, and noting any significant microbiome activity that might adversely impact the overall well-being of the culture. After about 4 weeks, those individual gametophytes grow large enough and are able to be distinctly told between male and female, which enables our team to isolate individuals with a goal of 2 males and 2 females per donor, and a goal of 20 donors for a population. From here, isolated gametophytes are suspended in vials and transferred to our germplasm bank, also sometimes called a biobank, which is very similar to the terrestrial method of seed banking. Currently, our germplasm holds over 20 geographically disparate populations of Nereocystis from across the Strait of Juan de Fuca and Puget Sound, which you can see here in this picture. In addition to being held at our lab here in Manchester, Washington, our collection is a replicate of the germplasm bank currently being held at the University of Wisconsin by the Felipe Alberto lab. Their team originally sporulated, isolated, and held the initial collection until we got our lab up to functioning capacity, and then they sent us a copy. Every time we add populations to our bank in Washington, we aim to simultaneously duplicate those gametophytes and ship them back to Wisconsin to ensure that there's more copies being held at both locations, this as a redundant system. Each gametophyte will be kept isolated in its own vial, with nutrients supplied only twice a year, under a 4-hour day length of isolated red light and at 5 degrees Celsius. This keeps the gametophytes, which you see here, in a slow but vegetative growth, not fully suspending their animation, but reducing it to a manageable, still alive state. Germplasm banking serves as a reliable storage of genetic material from across a wide area in case we see unexpected decline in wild populations. If a kelp bed were to seemingly disappear overnight, we can rest safely in the knowledge that there are copies of their genetics stored in our bank and that can be used for future restoration actions as deemed necessary. In addition, access to this genetic material can enable research and restoration of these populations without needing access to the wild material, which can become unavailable to severe and unexpected decline, like previously mentioned, as well as other reasons, like the seasonal patterns of kelp bed persistence and source production, which would make access to spores impossible during the winter in Puget Sound, similar reasons. Although gametophytes in the germplasm bank are in a stage of slow vegetative growth, access to this bank means that we can take samples from our collection and grow them out. This is done by taking small fragments of the gametophytes from within a population, which is transferred into the culture flask and into a designated culture room. In this space, the small brown specks you see in this photo are exposed to higher temperatures, up to 16 degrees Celsius, longer day lengths, 12 hours, and increased light availability, still isolated red light. The small fragments will grow into the larger pom-pom-like structures, which can then be fragmented and encourage high density growth. So they'll grow, fragment, and we can keep doing that. Additionally, our team makes enriched seawater media frequently, which will provide the nutrients the cultures need to further enforce that accelerated growth. Finally, we have folks in our kelp lab multiple times a week, which means we have our team monitoring cultures to ensure only the best looking ones are persisting, checking for the health of gametophytes, as well as microbiome activity within those cultures. This enables our team to intervene and toss any material that doesn't seem healthy in order to preserve the health of the overall culture, and then we can start over from germplasm if necessary. Gametophyte culture of this type allows our team to grow up dense biomass for restoration projects. When we reach a point of substantial biomass, these gametophytes will be settled onto a transferable substrate and undergo sexual reproduction, which produces sporophytes. While still near microscopic at inception, sporophytes are what will grow to become the large kelp forest-forming individual that many of us know. Our team has tried 2 methods so far for settling gametophytes on substrate. The first, which was taught to us by the Felipe Alberto lab, relies on inoculating very, very small strings of twine with a small volume of the genetic material and media, which uses gravity to adhere the gametophytes to the twine. These segments would then be spliced into longer spools of nylon, which is then transferred to in-water restoration sites. In this picture, you can kind of see them in the back, the small strings of fuzz use that method. The other is built off an industry method of binding gametophytes to the spool directly, using an algae-derived product known as sodium alginate. Through this method, a thick goop-like paint with living material embedded is applied directly to the spools and cured with a saline solution, which adheres the living material directly to the spool to grow. The spool in the foreground that you see here uses this latter method, as evidenced by the finger-like brushstrokes that we used the first time when testing it. Both methods have been traditionally applied to a nylon twine, which is readily unspooled underwater, easy to transfer, and used by divers who would be the ones deploying it. The spools of nascent sporophytes are transferred into aquarium tanks, which you can see in the background of the picture on the left, which are exposed to full spectrum white light, longer day lengths, and cooler temperatures than the gametophyte cultures until that brown fuzz seen in the picture becomes more pronounced, distinctly kelp-like, at which point they go out. The baby sporophytes settled onto the spools are then transferred out of the lab to any number of projects that we have going on in the field. The primary PSRF enhancement site is our restoration project at Jefferson Head, or Dokagwitz in Squamish, a site offshore of Indianola. Our team since 2019 has been testing different restoration aquaculture methods to learn about our practices and how to grow enhancement kelp forests. Over the years, we have learned much, including the seasonal nature of kelp growth, which starts as early as February, reaching the surface in about June, and dying back for the season at the latest in October. We've additionally learned about the density dependence of growth, trialing different seeding densities based on industry standards to determine if more or less dense transferred material has any difference in success of the overall kelp bed. This year, we're aiming to learn more about the difference between germplasm growth material versus wild spore-laden material to continue to understand and improve our lab methods to translate into wild in-water success. Key takeaways from our PSRF enhancement site have been applied to other enhancements. So far, we've taken our methods and collaborated with groups like the Squaxin Island tribe, who in 2022 experienced a rapid and unexpected decline in their natural kelp bed. Since last year, 2023, our team has grown and produced seed for the Squaxin Island tribe to transfer and monitor, demonstrating success last summer and looking forward to results from this coming season. Besides building on the foundation of knowledge that we've already established from our enhancement site, the lab is now also producing seed for more experimental transfers to learn even more about methods and potential restoration practices for the future. One project is our team's kelp gardening project, which engages community members in transferring and monitoring kelp growth. This project was developed to use minimally invasive transfer methods, lowering demand and need for a larger structural footprint, as well as for the need for highly trained scientists to keep track of growth and health of those adult sporophytes. This year, 2024, is the pilot year for this project, so far constrained to just 2 locations, with funding and potential to expand in the future depending on what we learn this year. Another project in the works is a reciprocal transplant project, again in collaboration with the Philippe Alberto Lab. This project aims to transfer kelp to two kelp populations, one from Puget Sound and one from the Strait of Juan de Fuca, into both of those locations. So 2 in one, 2 in the other. These experimental enhancements will be monitored by a team of divers measuring growth and survivorship to determine if kelp populations exhibit a genetic home field advantage or local adaptation within their home waters. This project also includes the creation of a hybrid of the 2 populations to explore hybrid vigor, or if a hybrid population of bull kelp appears to grow any different than the individual populations. In addition to what we already know and have learned from UWM and our other advisors, our team is constantly exploring new methods and protocols can be expanded upon. Our team is constantly learning from ongoing projects, noting new things that went well as unexpected turn of events to teach us what we can know for future rounds of seed production. The hope in capturing these lessons will aid our team for developing best practices, as well as informing collaborators on parallel projects to get a good sense of how growing kelp in our region can go moving forward. For other experiments, we're learning how to change the substrate that we transfer on. For example, for the kelp gardening project, we attempted to seed and transfer biodegradable twine, like those in this picture, testing that versus the naturally used nylon twine to see if we notice any difference. Besides just building off of our current methods, we're constantly exploring and new understudy transfer methods to lower the impact as well as increase scalability. One avenue of exploration, which we've pictured here, uses a molecular gastronomy method known as spherification, which creates these pods with kelp self-embedded that they might be able to grow within that sodium alginate matrix, the same that was previously mentioned. There's so much we have to continue to learn about this, how long it takes to degrade, how the kelp performs within that sodium alginate matrix, if it'll float or sink when put in sight. But if this method proved to be successful, it would require minimal to no project footprint to be installed, increasing scalability and lowering barrier to future restoration actions. We've also tested slathering natural substrate with that living paint, the sodium alginate and gametophyte material. If successful, this would reduce the need for installing anchors and the long glides that our current outplant projects require, and instead replicate wild kelp beds by adhering to native substrate like cobble and boulders. No presentation is complete without thanking all the people that make it happen. Our team has nearly doubled in size from what has been in the past. The fine folk here who are in this call or currently underwater make it all happen, so infinite thanks to them. And as well as to all of our partners who brainstorm all these projects, keep us moving forward, and direct a lot of the action of what we do in our kelp lab. So, thank you.
Thank you, Jessie. That was a fantastic virtual tour and background on your program. We have time for, we have a couple minutes and time for a couple questions. If they're out there, you can either raise your hand or put the questions in the chat. Yeah, that was really fascinating. Excellent.
Thank you.
See. Just check in the chat. I know there's a lot of praise coming in here, Jessie. I've been always so personally curious about what this lab is about, so I feel like it was really great to see how you're set up there. All right, I'm not seeing any hands or questions coming in.
Great. I'm happy to hang out in the chat if I get any.
Okay, it does look like there might be one question that came in around the kinds of results from the different strings, if you have that in yet.
Yeah. Hi, Tom. Yes, super great question. We don't know yet. We just transferred them to the water this year. So excited to find out. And that's part of the goal of monitoring, is to also check in on the difference in the different materials.
Well, I'm sure when you have results, you'll come back here and share out. We look forward to hearing
You'll see me. Certainly.
Oh, looks like actually Mike has their hand up.
One quick question. I was curious, when you put seed on a beach, you don't need an Army Corps permit like Western clam seed. Do you know if you would need? Do you know if you used the gametophytes in the alginate smeared on a rock in 20 feet of water, would you need a permit, or could this be done any place, much like seed enhancement for commercial clams and oysters? Thanks.
Yeah, great question. Yeah. For this first year of project, and I know Emily's in the chat, so she definitely has more thoughts on this. For this first year, we did talk to all regulators to see how they would feel about what we were proposing, just slathering natural substrate. And from talking with folks, they said that because we're not changing or adding anything, there was no need to go to that full scale of project. But that was also checked off by folks because we said we're just doing Bainbridge Island right now at this point. So if it went to a larger scale, there's always a potential for that, and that would be a conversation to have down the line.
Thanks again, Jessie. And up next, we have Caitlin, who is from the Puget Sound Institute at UW Tacoma. And welcome. You're presenting on your kelp and eelgrass threat assessment modeling project. Great. The slides look great. I'll hand it over to you, Caitlin.
Okay, thanks, Bree. And thanks, Helen, for slotting us in on the agenda today. My name's Caitlin Moggle. Like Bree said, I'm at the Puget Sound Institute, and I'm talking to you today about a project that I'm collaborating with Wendell Raymond at Washington Department of Fish and Wildlife on, and that is to rate threats to kelp in Puget Sound. And pictured here are the folks that we engaged with on this project, and you'll recognize a lot of the faces in this group, and I'm sure I've noticed that a bunch of you are on the call today. So thank you for being here, and thank you for your participation already in this project. Apologies to those of you who were at the Kelp Node meeting last week. This will sound familiar, and then for those of you planning to attend the PSEMP Nearshore Workgroup next week, apologies also because either Wendell or I will be presenting to that group as well. But just trying to get out the word on this project to a wider audience. So thanks for your patience. This work that I'm talking about is part of an overarching project that is looking at the distribution of current and future risk of anthropogenic and climate change threats to both eelgrass and kelp in Puget Sound. It was part of a Puget Sound Partnership scientific research grant. And essentially what this project will do is to perform a spatially explicit cumulative risk assessment of both current and future threats to eelgrass and floating kelp in Puget Sound that can be used to evaluate kind of the distribution of risk across the landscape in Puget Sound, or seascape, really. The motivation for this study was a project recently out of Australia where they did essentially this. They mapped the risk of anthropogenic and climate change threats to seagrass habitats around the continent of Australia. And so we're planning to do something similar, which is taking maps of the habitats for both eelgrass and kelp, layering on top of those maps, describing different threats to the habitats, and then calculating current and future risk. So what they did in Australia in this paper that came out a couple years ago was to characterize high, medium, and low risk areas for seagrass around the continent of Australia. And then you can see they've kind of rolled that up into regions and described how much of the habitat is in high, medium, low, or no risk categories based on their maps. So the way that we were defining risk in this larger project, in this cumulative spatial risk assessment, is basically exposure. So that is overlap of the threat or multiple threats with the habitat. A consequence of each of the individual threats to the habitat. So basically the species vulnerability to a given threat. And the magnitude or intensity of that threat. And that will come from spatial data layers describing the intensity of the threats across space. So an important component of this definition of risk is the consequence or the vulnerability. And that is kind of a numerical, so semi-quantitative score describing how vulnerable the species is to that given threat. So overall, right, so this is kind of the framework for the project. We have the habitat extent maps. That information exists and is publicly available. Defining what are the threats to eelgrass and kelp, and that work has been done already. I'll touch on that in a second. the exposure to the threats, so those are the maps defining where these threats occur across space, and then that ranking of threats, or the kind of semi-quantitative score describing vulnerability. And so I'm going to focus on these three things today. We've basically completed these steps and are looking for feedback from you all. So for eelgrass, there was a great report that Ron Tom led in 2011, where a group of experts got together to define the stressors to eelgrass in Puget Sound, as well as to rank essentially their threat to eelgrass. So this purple arrow indicating the column where they have a quantitative threat score to eelgrass. At the same time, they also ranked our level of knowledge for each of those stressors or threats to eelgrass, and so ranking where we have more or less information about that threat. So Wendell and I set out to do something similar to the process that Ron Tom led in 2011 for kelp in Puget Sound. And we're building on some great work from a couple years ago that Jordan Hollersmith led, where they developed a conceptual model of the threats, or they called them pressures, for kelp in Puget Sound. So we have this list here of 9 pressures for kelp in Puget Sound. And this was the basis for our ranking or rating exercise of threats to Puget Sound kelp. So what we did, or what we set out to do, was to bring together a group of experts on Puget Sound kelp and ask them to rate these different pressures to kelp. And in conversations with them, we ended up with actually 10 stressors. So because we broke this nutrients pressure into both high nutrients and low nutrients as kind of separate potential stressors or threats to kelp in Puget Sound. So we had 10 pressures or stressors, and then those were rated by 6 experts who were in the photo on the first slide. So folks that you know and probably love. So in the scope of this project, the original project was to do Nereocystis sporophytes in Puget Sound, but in conversation with that group of experts, they said, while we're at it, we should rank or rate these threats for not just Nereocystis, but also our best understanding for Macrocystis and for kind of the understory kelps as a single grouping. In addition, because we know these species have 2 life stages, we think we should separate out the sporophyte and the gametophyte life stages. And while we're at it, we should think a little bit more broadly outside of Puget Sound to include the other Washington coastal areas, so the outer coast and the Strait of Juan de Fuca. So they expanded the scope of the initial project. So what we ended up with was a massive spreadsheet with drop-down boxes where the experts were asked to rank these or rate these different stressors for the different species and life stages, including these different characteristics about those stressors. So the magnitude of the stressor, the spatial extent, the timing, the ability to reverse the stressor, the trend over time. So whether that stressor is expected to increase or decrease or stay about the same into the future. And then the depth extent of the stressor. So is it acting at the surface or the bottom or throughout the water column? So in total, when they ranked the 3 species, so macro, nereo, and understory, the 2 life stages, 10 stressors, and 6 characteristics for each stressor, and then they ranked both the kind of the rank, so the level of vulnerability, and also the certainty with using these different drop-down menus. There were 840 cells for each of the experts to fill in. So this was a really big lift. But we ended up with a lot of great information to work with. So this is what the final table looked like. So these are cells that are filled in with the work group. So those 6 experts, the mean value across the 6 experts. So again, those characteristics for each stressor, they had the different species and life stages. And we calculated the means based on their individual scores. For the rank values, that's like the intensity of the characteristic. We excluded any zeros. So the experts were allowed to say unknown for that rank category, meaning they literally had no information to go on. And any rank that they would give it would be a total guess. So when calculating those means, we excluded zeros from this, but we kept track of the zeros. So how many times people said, I have no idea, because that indicates a potential gap in our knowledge. For the certainty scores, that's like how certain we are about the magnitude or the reversibility or the spatial extent of this stressor. We included zeros in our calculations of the means across the work group members, because an unknown certainty should be included in that quantitative score. So there are a bunch of different ways to kind of slice and dice this information, and I'm just going to show a couple plots and figures to talk about the high level takeaways, but happy to dig into more, and also happy to share our report from this kelp threat rating process and allow people to dig into it more on their own. So from that magnitude rank score, things that came out on top, kind of regardless of species or life stage, were temperature, substrate change or sedimentation, and low nutrients. Those were considered important, particularly important threats or stressors for the kelp species and life stages. At the bottom, so kind of lower importance, were things like epiphytes and contaminants. And then there were lots of things that came out in the middle, and those were kind of more species and life stage dependent. Things that had largest variability, so across the 6 experts that were rating these things, things that were more variable were the nutrients, both low and high. People tended to rate those a little bit differently. And then epiphytes also had some variability across the work group members. Things that had low variability, so everybody kind of generally agreed upon, were salinity and temperature. We also calculated, and this comes from the way that the Ron Tom eelgrass stressor ranking report was done, was they calculated a mean of the characteristics of magnitude, reversibility, spatial extent, and timing. And so we're calling that kind of the total stress associated with a given stressor. So for that, things that were high were temperature, low nutrients again, and then epiphytes, but specifically for understory gametophytes. Things with kind of middle level total stress scores were substrate change and sedimentation, algal competition, and water clarity. And then contaminants, again, kind of coming out on the lower end, as well as high nutrients. Again, some things had more variability between the experts, and things in this case were epiphytes on both macrocystis and nereocystis, and then gametophytes in general. Their responses related to the gametophyte life stages tended to be more variable across the work group members. Things that had less variability and there was more agreement upon were algal competition and salinity. Here's a plot showing that rating, the numerical rating, and then the level of certainty is on the x-axis. So rating on the y-axis, certainty on the x-axis, And this is specifically that total stress or the combined score of several characteristics for Nereocystis in the sporophyte life stage. And these dots are colored by the individual stressor. You'll recall that temperature, this gray dot, had both high certainty and a relatively high rating. That is true for the Nereocystis sporophyte responses. And then on the other end, so lower certainty and lower rating were contaminants and epiphytes. So you'll see that, as well as high nutrients and some other things falling out in the middle. So one interesting takeaway is that there's kind of a seemingly a positive relationship between the rating that was given and also our level of certainty. So that's an interesting relationship that we saw kind of across species and life stages. This is that same plot that I just showed you, but all of them. So all of the 3 species, understory on the bottom, Nereocystis and Macrocystis, and then sporophyte life stages on the left and gametophyte life stages on the right here. And the stressors are color-coded. So the plot that you just saw is this middle left-hand column, the Nereocystis sporophyte, but now you're seeing that same plot for the other species and other life stages. In general, like I said, the sporophyte life stages have a little bit more certainty and a little less kind of spread across the stressors. The gametophytes have less of that kind of positive relationship between certainty and rating. And also both the certainty and the rating are a little bit more spread out for the gametophyte life stages, indicating that we have less information to go on for gametophyte life stages. Okay, so as I said, there's lots of ways to kind of cut this and display it, and we have more shown in a written report that we're happy to share with anyone who's interested. Let me just touch briefly, and then I want to make sure there's time for questions. So the next step that we're working on right now is collecting maps of those stressors related to kelp, describing how they're distributed across Puget Sound. We'll then match those with maps of the habitat to look for overlap. This is probably hard to read on your screens, but again, we have it in our written report and I'm happy to share it. So we've been collecting data layers describing those stressors or kind of proxies that relate to those stressors. So for algal competition, we might relate proxies related to temperature or nutrients that we know are likely to increase the level of algal competition. For contaminants, we're creating maps related to industrial land uses, the presence of oil and gas production or transport, and then vessels that might be transporting or exposing the habitats to different contaminants. So lots of examples as we go through here. I just want to talk quickly about some. So we're looking at current threats, but also future threats. So things like increased temperature, changes in salinity. And so for that, we are relying primarily on some of the models. So the Salish Sea model, or the live ocean model, where they've done projections into the future under climate change scenarios. And we can leverage those modeled outputs to understand how threats might change into the future. With that, I'll stop talking and hopefully there's some time for questions. And again, happy to follow up with folks afterwards or share our report and follow up after you've had a chance to dig in. Thanks.
Yeah, thank you, Caitlin. What a comprehensive project. I do think we're short on time here for questions since we have so many presentations, but I encourage folks to put questions in the chat. And definitely sounds like there's a report, definitely if you want to get that report, make sure to reach out and connect with Caitlin. Thank you again for sharing out on this great project.
Absolutely. Thank you all.
Next up, we have Julia Ledbetter with DNR, and Julia will be presenting on the long-term kayak monitoring of floating kelp in the Puget Sound, and these are the results from the field year 2023. Julia. Again, as I've mentioned to other folks, you have 20 minutes, so if you want to use most of it for your presentation, that's fine, but I'll give you a 3-minute warning if you want to allow at least time for a little bit of questions.
Okay, great. Thanks, Bree. Hi, everyone. I'm just going to give some highlights of this long-term kayak monitoring report that Helen and I just finished, and it's now on our website. The link is also on the agenda today. So as we know, floating kelp forests are highly productive habitats that serve as refuge and foraging ground for many species, and they also provide important ecosystem services. At DNR, the Nearshore Habitat Program monitors floating kelp with a set of nested monitoring efforts that use multiple survey methods, including fixed-wing aircraft, UAS, and kayak. So the statewide floating kelp indicator that Danielle showed earlier shows the status of floating kelp differs by subbasin. And you can see that South and Central Puget Sound, which are in red on the map, are two areas of declines in floating kelp. In these inner basins, we use kayak-based monitoring for a lot of our monitoring efforts here. And kayak monitoring successfully detects narrow, low-density floating kelp forests that are often missed by remote sensing. And they're also a common bed type in South and Central Puget Sound. And kayak monitoring also allows us to track additional parameters such as depth distribution. So our new report includes our kayak monitoring results through field year 2023. It's a long report, so be prepared. But in the results section, there first starts with summary results for bed area and bed depth, and then after the summary results, we have site level results for all the sites included in this report. So the sites, we have 20 sites included in this report, and they're all on the map here. 13 sites are core sites, which are in orange on the map, and there are ongoing annual monitoring locations that are included in the floating kelp indicator. There also are 7 focus sites in this report, which are in purple, and address project-specific questions, and they vary in monitoring time span from about 1 to 5 years. Most of the sites you can see are located in South and Central Puget Sound, but we do have some focus sites that are located in other subbasins. So at all of our sites, we have a defined site boundary, which is the yellow boundary on the map here, and then 13 across shore transects, which are in pink on the map. So for bed area, we collect 3 perimeters within the site boundary during each monitoring effort. Along each transect, we also collect minimum and maximum bed depth and density and percent cover measurements. We also collect water quality parameters at each site. So this report includes the bed area and the minimum and maximum depth data, but does not include our density, percent cover, and environmental measurements. So what I'm going to do for this presentation is go over some of the summary results and then highlight a few of the sites. So for bed area, we classified trends at core sites over 3 time periods: the entire data record, 5 years, and 3 years. And the length of the data record varies by site from about 3 to 10 years. We found that severe declines and total losses continue to dominate the long-term trends of floating kelp in South and Central Puget Sound. So if we look at this map that shows the entire data record, all the entire data record trends, we see that it's dominated by these declines and losses. So the map shows the location of each of the core sites, and they're colored by trend. So 4 sites we found experienced total loss, which are the red dots on the map. And they are Briscoe Point, Devil's Head, Wing Point, and Point Jefferson. 2 sites have decreased, which are in orange, Squaxin Island and Fox Island. And then 1 site has no trend in blue, which is Salmon Beach in the Tacoma Narrows. If a site had less than 5 years of data, the entire data record trend was limited data, which are the gray dots on the map. So in contrast to the declines and losses seen in the long-term trends, stability or increases in bed area were common in recent years. So I have a map for that as well. So if we look at the 3-year trends, on this map, 4 sites were classified as increasing, which are the green dots on the map. So Day Island, Vashon Island, Owen Beach, and Lincoln Park. Oh, sorry, in Hansville. 4 sites had no trend, which are in blue. And those are Squaxin Island, Salmon Beach, Owen Beach, and Lincoln Park. 1 site was classified as decreasing, which is the orange dot at Fox Island. And then 4 sites had no kelp, which are the black dots on the map of Briscoe Point, Devil's Head, Wing Point, and Point Jefferson. So if we move from looking at these maps of trend designations to the graphs of the bed area for these sites, these map graphs show changes in bed area over the full data record with kelp bed area on the y-axis and year on the x-axis. So you can see the decreases at Squaxin Island and Fox Island over their entire data record. In 2023, Fox Island only had 2 plants remaining. Briscoe Point, Devil's Head, Wing Point, and Point Jefferson are the sites that have lost kelp, and you can see that they're symbolized by the red X's on the graph. And then the recent increases in bed area that I mentioned can be seen at Day Island, Vashon Island, Magnolia, and Hansville. And actually, Magnolia quadrupled in size between 2022 and 2023. We also looked at the proportional change in bed area relative to the previous year. So for this graph, the proportional change in bed on the y-axis and the year range for the change is on the x-axis. So Squaxin has the longest data record, which are the blue dots on this graph. So on the left side of this graph, you can see that Squaxin had a consistent proportional decrease in bed area through each of those time steps. And for the entire period between 2013 and 2017, which is on the right side of the graph over here, there are floating kelp bed area decreased 82 to 100% at 4 sites in South Puget Sound. So Briscoe Point, Devil's Head, and Fox Island were only surveyed in 2013 and 2017. So that's why we can only graph the change over that time range. Since 2020, we've expanded the annual site pool in South and Central Puget Sound, and this allowed for comparison of year-to-year changes across 9 sites with floating kelp present. And those 9 sites are represented in these box plots. And the diamonds on the plot represent the mean, and the lines on the box plot are the median. And the outliers are labeled by site. So between 2020 and 2023, sites generally show variable year-to-year changes rather than a strong synchrony between sites and years. However, there are some site scale patterns that are evident. Across all the time periods, Fox Island decreased. You can see Fox is one of the outliers on all 3 of these years. In 2022, Squaxin Island decreased dramatically. And then between 2022 and 2023, Squaxin Island and Magnolia Bluff increased, had large proportional increases, so 525% and 300% respectively. So moving on to bed depth, we found that the depth distribution of most of our floating kelp forests was shallow, with some notable exceptions. So this graph shows the depth range along the transects. The maximum depth is on the left side of the graph, and the minimum depth is on the right side. And the sites on the x-axis go from south to north. So bed depth along these 13 transects varied by site, but it ranged from -0.2 meters to -13.8 meters. And the deeper mean maximum depths occur closer to oceanic influence, so freshwater bay, which is this spot right here, and closer to in areas of intense current mixing, which is right here at Salmon Beach. The shallowest mean maximum depths were found at Squaxin Island, which was only -2.4 meters, and at Beckett Point, which was -2.3 meters. And you can see from this graph that the mean minimum depths were less variable than the mean maximum depth. In addition to depth distribution was also estimated by comparing the bed area perimeters to model bathymetry data. So this graph shows the percent of bed area per 1 meter depth bin, and it's colored by site. So you can see that the bed footprint varied by site, and that most of the sites have a fairly shallow bed footprint. At 10 of the 16 sites, more than 85% of the bed footprint was shallower than -6 meters. And Freshwater Bay, had the deepest proportion, which had 70% of the bed deeper than -6 meters. Okay, so now I'm going to move on and show a couple of the site level results. So in the report, each site section includes information on the site location and current monitoring efforts, a bed area map and graph, minimum and maximum depth distribution, depth distribution using the model bathymetry, and then an interpretation of site level results. So I don't have time to go through all of the 20 sites in this presentation, but I'll highlight just a few sites. So first is Squaxin Island, which is the innermost floating kelp bed in Puget Sound. So the bed area at Squaxin has decreased over the entire data record from 8.8 hectares in 2013 to just 1.9 hectares in 2023. In 2022, the bed decreased to just 85 plants, which is the blue perimeter on the map. However, in 2023, the bed area partially recovered to 1.9 hectares, which is the yellow perimeter on the map. And this partial recovery was the natural bed, not the restoration effort that Jesse mentioned earlier. So this graph shows the minimum and maximum bed depth along the transects. The purple bars represent the deep edge of the bed, and the red is the shallow edge. And you can see that the deep edge of the bed has contracted from -4.4 meters in 2013 to around 2.4 meters in 2023. In 2022, the bed was so small that there were not enough kelp along the transects to collect minimum and maximum depth, but depth was collected at each plant, so that was a yellow box on the screen on the graph. And then finally, this is the depth distribution estimated from the model bathymetry data. And it shows that there is a peak depth distribution that occurs shallower than 3 meters in all years. And you can also see from this graph that you can see the contraction of the deep edge of the bed as it moves from 2013 to 2023. The next site I have is Magnolia Bluff, which is located in Elliott Bay, just west of Elliott Bay Marina. And the bed area at Magnolia has increased over the 3-year time period. And it increased from 0.6 hectares in 2022 to 2.3 hectares in 2023, which is a 4-fold increase. So the bed perimeter in 2023 encompassed the previous year's perimeters on all sides and extended further west. So 2023 is the yellow perimeter on the map. However, the density was much lower in the expanded perimeter, 2023. So here is the graph of the minimum and maximum bed depth from the data on the transects. So depth is on the Y and years across the X. You can see that the maximum depth was deeper in 2023 than all the other monitoring years. And the minimum depth shows a much wider variation in 2023, which is due in part to the deeper clusters on the western portion of the site. And if we look at the depth distribution from the estimated modeled bathymetry data, it shows that the distribution peaked deeper in 2023, so closer to -5 meters versus -3 meters in previous years. And then the last site I have is Lincoln Park, which is located in West Seattle. And this kelp bed has remained very stable that I'm monitoring since 2020. The bed has 2 very distinct lobes that are often separated by a small gap in plants. There's a wide range in maximum depth along the transects at this site, which can be attributed to spatial variation. And I'll show you some of that spatial variation on the next slide. You can also see that the minimum depth does not show the same variation. And then if you look at the modeled bathymetry, or the depth distribution from the model bathymetry, it shows a very similar pattern in all the years. So if we look at the spatial variation of the depth at Lincoln Park, this map and graph visualize that spatial variation. So in the graph, the depth is on the y-axis and the x is the transect number, which is represented also on the map. The minimum bed depth is represented by the circle on both the map and graph, and the maximum depth is the triangle. So on both figures, you can see that the maximum depth is deepest within the 2 main lobes of the bed, usually reaching about -6 meters or deeper. And then it was much shallower along the boundaries of those beds, approximately -2 meters or shallower. And then each year, 5 transects along the boundaries of the main beds so transects 1, 2, 6, 7, and 13, only had one plant present, which was recorded as both the maximum and the minimum depth, or the deepest and the shallowest plants are very close together. So this could explain that wide range in maximum depth that we saw on the previous slide. So unfortunately, we don't have time to go through any more sites, but the report has all 20 sites with all the data that we have. So check out that report if you want more information on the various sites. And with that, I'll take any questions if we still have time.
Yes, thank you, Julia. That was great. We do have time for several questions. And it looks like we've got one coming in from Tom in the chat.
Okay, I'm trying to find my chat.
Oh, okay. You want me to read it off?
Okay.
It's been, oh, you got it? Okay.
Hold on. Cold Spring. We have not been, I don't know if it's been a good help you. We have not been out yet to do any of our surveys, so I'm not sure if it'll be a good help you or not. Hopefully. Hugo, how we measure bed increase. So for our trends, we used, we ran simple linear regressions on our bed area data, but also used expert opinion and just our knowledge of the site to kind of override any. Some of our sites only have a few years of data, and so a linear regression only gives so much information. So we kind of compiled a bunch of different information to then decide on our trends for increase versus no trend.
Great. Any other questions out there? You can raise your hand or put them in the chat.
This one, we've seen depth limits on related to availability of substrate. And we don't, since we're on the kayaks, we can't actually look at any of the substrates. So some of these sites are also reef check sites, which will have some substrate data, but we currently haven't looked at that yet because we're on the surface of the water. And then Celine, is there any satellite data to cross-examine? We haven't used satellite data because a lot of these beds are really small and sparse and they're hard to see via satellites, but a lot of these sites are paired with drone surveys, which Tyler will talk about next.
Great. Well, I think that might be the most fantastic segue possible. Thank you again for presenting, and look forward to hearing what you find out this year.
Thanks.
So Tyler is up next, also with DNR, and presenting on some monitoring using multispectral UAS. Welcome.
Okay, hopefully everyone can see that. Thanks everyone. A lot of great stuff today. Everyone's hanging in there. It's a lot of information. So as Bree mentioned, my name is Tyler Cowdrey. I work for the Nearshore Habitat Program. And today I'll be talking about our work mapping floating kelp canopy with multispectral UAS. So from the information I'm aware of, Helen can correct me, I think Nearshore and the Aquatics GIS unit have been exploring the use of drones for habitat mapping since at least around 2016. Maybe it was even a little bit before that. But my work kind of in this realm began in 2020 when I was a master's student at the Evergreen State College. And I worked with Nearshore on my thesis, which was a proof of concept mapping floating kelp canopies with off-the-shelf consumer drones. And then in 2021, this work continued and we got an interagency agreement with the Northwest Straits Commission. And that project specifically was comparing multispectral drone imagery and conventional plane-based imagery with a near-infrared camera. And we assessed kind of various trade-offs between the different platforms. That's kind of all I'll say about those today, just as some context, but encourage people to check out both of those documents for more info on those projects. So everything I'll be sharing today then is from a report that Danielle and I recently published. It can be found on the DNR website at the link at the bottom here. So those previous two projects I mentioned were very successful at mapping specifically Puget Sound bull kelp canopies with drones and near-infrared imagery. But the projects were inherently kind of exploratory in nature, somewhat limited in scope. And so this report really summarizes our efforts over the past few years to develop a repeatable index-based classification workflow so that we can expand the UAS work for monitoring kelp forests throughout Puget Sound and beyond in the state. So in the report, we include results from 18 surveys across 6 different sites in Puget Sound, conducted in 2021 and 2022. 16 of those surveys were part of survey pairs, we call them, where we conduct the survey in the shoulders. Let me get my pointer. In the low tide, kind of shoulders around low tide in the ebb and flood periods. And we use those pairs of surveys to start to get our arms around questions of variability and uncertainty in these survey methods. And some of our research questions are listed there as well for this report. This is the drone that we used. It's a Phantom 4 multispectral drone that captures imagery in 5 spectral bands, they're called, 3 visible and 2 kind of in that near infrared range that we can't see with the naked eye. And in terms of our classification workflow that we developed, we start by masking, we call it the bed, essentially just isolating the areas in the imagery where floating kelp is present in order to conduct image classification. These polygons, when we do the masking, actually can double as rough bed extent estimates in and of themselves. So when we draw these, we kind of follow a similar threshold requirement to the kayak-based surveys, which is 25 meters between individuals to be included within one bed polygon. And so you can see here, this is a 25-meter grid displayed over some survey imagery, and you can see a few of these individuals floating off further away than 25 meters, so we exclude them from that bed mask. And then on the right here are just some ways that the imagery can be visualized differently using those 5 spectral bands. So the top left is kind of just your standard RGB. There is an artifact in these images with this band, just has to do with kind of the light characteristics interacting with the orientation of the drone. So those come out when we do the classification further down the line. But yeah, so the top left is kind of your RGB, and then the rest of these are various combinations of visible and near infrared information. So by toggling between these, we can kind of get a better picture of where the kelp is present to assist in the extent masking. And then from there, we use what's called an index-based classification using thresholds. And so just kind of the real basic summary of this is that we start off and we have our imagery that we have masked using kind of those different ways to visualize. And then we clip that imagery down to that mask. So we exclude areas where there's no kelp present. And we run a vegetation index, they're called. In this case, we're using BNDVI. And so this takes the blue values and the near infrared values and compresses all that data down, or flattens it rather, into values between -1 and +1, 1 representing a very high near infrared signal and low blue, and -1, vice versa. And you can see here that that it really makes the kelp kind of pop just visually even. And that's kind of what those indices are designed to do. And then from there, if you imagine, a histogram of values between -1 and 1, we can select a specific threshold where everything above that threshold is kelp canopy that we classified. So we do that, we select a threshold, and from there we can get canopy area estimates, percent cover estimates within that bed extent polygon, and we can use the canopy map even to aggregate bed area. Still kind of working on that last one, but so pros and cons to this approach. The biggest pro is that the workflow can be essentially entirely automated. Some of those previous projects relied on really laborious training data, drawing, literally taking the imagery and drawing around areas that are kelp and water, and then using that to train a model. So that's a big improvement in terms of scalability. Also, using kind of a standard index across all these surveys allows us to compare between sites, between surveys in a kind of semi-objective way. The index values are really dependent on various environmental factors, but it helps in that regard. And then probably the biggest limitation still is the selection of the threshold does introduce some subjectivity. And I'll talk about that a little bit more on the next slide here. But we tested using an automated method to select the thresholds, and we're finding that pretty consistently it overestimated the amount of kelp canopy just based on kind of our visual assessment. That automated threshold is a pretty standard one. It takes a range of values along a histogram here, and it basically runs trial and error, and it looks at the variability within groups based on where the threshold is drawn, and tries to minimize the within group variance and maximize the between group variance simultaneously. So yeah, the hypothesis there is kind of just that a lot of the kelp forests that we're mapping in this way are very low density. As you can see here, if you just look at the blue histogram here, that represents the BNDVI values within a clipped survey area. These are all water pixels, and these are all the kelp pixels. So you can really see how it's skewed towards a lot of water pixels. So still kind of working on that part of it to see if maybe there's other ways to pick the threshold in an automated way, if there's ways we can mask the imagery differently to improve that. But for now, we are kind of trial and error testing a range of index values, assessing how well that maps the canopy, and then selecting based on that. And I'm definitely going too slow here, so I'm going to keep chugging. So as I said, this kind of introduces a bit of subjectivity. And on the right here, you can see kelp canopy area within one of these surveys as it relates to where we draw that threshold on the histogram. And in some cases, the effect is insignificant. In a lot of cases, it is more meaningful. So we kind of took the approach of identifying what we call the plausible range of threshold values and then using the midpoint. And this kind of gives us, you know, what people are familiar with kind of a single data point and a rough uncertainty around that when we do our assessments. I'm going to skip this. Okay, so on to some results. Sorry, yeah, just to state explicitly that, you know, we kind of view this as a source of uncertainty of 2 that we evaluated in the report. I think I did say that. So the second source of uncertainty, and also kind of a result in its own right, is looking at the variability between the paired surveys. Again, in a lot of cases, there was not a huge difference between paired surveys. The canopy looks very similar, you know, about an hour apart. You know, that's kind of what we would expect. But there are cases where between the paired surveys, there were significant differences that we documented. So on the left is an example of how the bed extent polygon shifted between the paired surveys at Owen Beach. And this has to do with the really strong tidal currents as the tide comes back in. And similarly at North Beach, these are 2 paired surveys. And you can see in the first one that we kind of hit like true slack. So all the blades were drooping, not a lot of canopy to be seen other than the stipes and the bulbs. And then in the second survey, tide's coming back in, current picks up, and all the blades extend. So this actually resulted in a much higher canopy area estimate. So really site dependent, just more contextual information for when we plan surveys, trying to hit consistent conditions each time. And so when we put all this together, you know, what does that look like? Our end goal here is to do long-term monitoring, obviously. So we need to be able to take these sources of uncertainty, use it as contextual information, and then make assessments. So in the report, we had 4 sites with data between the 2 years that we looked at for change. The 2 on the bottom here, Owen Beach and Vashon, were both deemed to be no change based on the results. You can see here as I was kind of saying, the midpoint estimate and then the high and the low, you know, kind of classification uncertainty bounds, as we would call them. In the top left, Lincoln Park, the data does show a decrease, but when we re-examined the classification results, there actually was a lot of false positive classifications due to like floating rack mixed in with the canopy. So that kind of nudged that estimate from 2021 down just enough that we decided to also call that no change. And then finally in the top right, North Beach, here there was a decrease that exceeded the 2 sources of uncertainty that we were looking at in this report. So at a minimum in the data, we saw a 45% decrease in canopy area. And there's a couple asterisks on that, but it was significant enough that it was a reason for concern and for us to keep surveying here. And then the final kind of type of result that we present in here is we actually took the survey results at each site and we subdivided the site into rough quadrants, we called them, divided by a -3 meter bathymetric contour and roughly halfway across the site by shoreline length. And then we repeated that same kind of assessment framework just within each quadrant. And so you can see here, this is the North Beach results. The decrease in canopy area really was heavily concentrated kind of in the shallow area there. And yeah, so you know, the dividing into quadrants is kind of just one example of how we can subdivide sites. We're thinking about, you know, eventually we could divide each site into more grid cells and look cell by cell. With this resolution of data, you really have a lot of ways to slice and dice it. And one interesting thing about the quadrant method here too was that the two sites, Owen Beach and Vashon Island, that Vashon Island East, I should say, where we determined there was no change based on the overall site, there actually was in each of those cases one quadrant that that appeared that there might have been an increase in canopy area after all. So it kind of revealed how looking at subsections of sites, you might get different results than looking at the whole site. Okay, and then finally, just key takeaways here. The project was pretty successful in that it, in terms of creating that kind of scalable, repeatable workflow. So that's really encouraging for us to be able to start scaling this up. Going out and continuing to do surveys at many of these sites, creating a longer term data record, and looking for long-term change. And yeah, future work, always looking at ways to improve our classification workflows. So we'll continue kind of fine-tuning this that we present here. We're going to keep doing surveys at most of the sites that that I've been going out to these past few years. Our program is looking at some new sites this summer. So there's a little bit of kind of just a limitation on how many good low tide days we have. So may try to go out and visit some of those other news sites to get fresh data there. And then we have two projects in the works. One's already pretty well underway. We have an interagency agreement that my colleague Bart Christian's leading with Tim McClure being the UAS pilot. And they are going to go out this summer and survey all of the floating kelp forest canopies in the central basin of Puget Sound. So no big deal. And that's chugging along. We did a couple surveys last year to start chipping away at that, and really excited to get data over this entire area. And then also Julia has been working up from the kayak work some percent cover and density data along transects that we hope to compare to the drone imagery as well, and start to really get a sense of how comparable those metrics are and if they can be used interchangeably in certain ways. And I think that's everything I have. So I don't suppose there's time for questions, but happy to answer any in the chat.
Thanks, Tyler. That was great. Yeah, we have time for maybe one question. The rest will need to go into the chat. So I think there is, looks like a couple questions have come in. Let's see. The first question,
Scott is first.
Yeah, go ahead. Take the one from Scott.
Yeah, so Scott's asking about the Kelpomatic, which is this really amazing classification tool that the Hakai Institute developed. It's a machine learning image classification tool. It was trained specifically on RGB drone imagery. And in the past, we tested it on our kelp forests, and sometimes it worked really great. And there were some cases where it didn't, but they have developed now a new version of Kelpomatic that uses multispectral data. So yeah, it's on the short list to start kind of doing some tests with that and see how it compares. Just intuitively, the multispectral data, as I was kind of showing with the ways to visualize the imagery, you get so much better differentiation between the water and the kelp using those near infrared bands. So yeah, I think that's really promising. And eventually, this all eventually is going to go to machine learning, and it'll just be black boxes that we train, and we throw stuff in and we get results out and kind of assess them, and then free ourselves up to do hopefully a lot more interesting analyses. So yeah.
Thanks, Tyler.
Okay, thanks everyone.
Yeah, it's great. And for others, feel free to put additional questions in the chat, but we are going to move into our last presentation. Alondra. Yes, you're here. Great. Alondra is doing the postdoc here with the University of Victoria, and I will just pass it right over to our international partners here.
Thank you. I would like to check if everything looks all right.
Looks great. Yeah.
Excellent. Okay, thank you so much for inviting me to present this work. So this is the first part of my postdoc. I recently finished it with a more complete overview of what is going on in the complete Salish Sea, but this is the first part, and this is a recently published paper, and you will see it. If you have seen it already, it's published in Frontiers of Marine Science. Here is the title, and this is the area where this paper is located. So all the rest of the Salish Sea, I mean in British Columbia, will be covered in a separate paper. And I would like to ask for patience for all the people that have seen this presentation before, because I will repeat myself again, but for many others it will be maybe the first time. So I hope you find it interesting, despite this is a very long meeting. I hope it's not too bad. So the objectives of this paper is to show what are the trends of kelp in this area that I just highlighted over the last almost 20 years, and also looking at the coverage in a sentinel site located in the Strait of Juan de Fuca, because we had more data from that area for at least 5 decades. I think maybe this is the very first paper that covers the 5 decades of data. And the other part of the project was to look at the environmental drivers. So the trends in nearshore sea surface temperature, what were the frequency and intensity of marine heat waves, and the wind. So to separate the area and the time, we split the coastline into clusters, and the temporal frame was split into periods. So what does this mean? So in the cluster idea, we separated the coastline for their abiotic characteristics. So in first place, we have the first cluster that is highlighted here in blue, and is representing the coldest areas with the highest currents and also the highest fetch. Cluster 2, that is here highlighted in green, is a bit warmer and a bit more sheltered or protected. So you can see it around here, southern Vancouver Island, and the more enclosed areas of the Juan de Fuca. Cluster 3 is all the coastlines that are looking at the Strait of Georgia, and they're also exposed. They have high fetch, but has higher temperatures. And the cluster 4 is the warmest areas, and they are the most protected and sheltered areas, and they are here highlighted in orange. And we assembled all the information of kelp using very high resolution imagery. The very high resolution imagery, this is not as fine in resolution as drones, but is not as wide as Landsat. So it has like less than 6 meters of spatial resolution. It's not so frequent. So as we assembled everything that we had available and discarded a lot of data that was in high tides and in off-peak season. We tried to get everything like low tide and in the summer season, and we did a lot of pruning of all the the noise to get like the best data available. For that reason, we have more spatial coverage of this area, which is the Greater Victoria area, that covers 16 years of data. The cluster 2 covers 12 years of data, cluster 3, 11 years of data here, and cluster 4, 8 years of data. And we also see that there is a trend that in general, cluster 1, the blue areas have more spatial distribution of kelp in general, and cluster 2, 3, and 4 are decreasing in their total area ever mapped. The second part of this project was separating the years and aggregating them into periods. So the periods were conceived by the fluctuations of PDO and ONI, or El Niño. So the years that are El Niño, or warmer years in the Pacific Ocean, they look in this plot as red years. And PDOs also have these fluctuations, and so we separated them according to Z scores, and the years that are in red are also positive years for PDO. So they went along, they had the same kind of similarity. So we had these periods from 2002 to 2006 was considered a suboptimal time or period because we concentrated the highest the values of these indices. From 2007 to 2013 was considered an optimal period because the PDO and ONI were negative. Then they were positive again and was considered a suboptimal period, and is also called as the blob. For everyone here, I think they all know what is this period about. And from 2020 on, we have a new optimal period in which PDO and ONI went negative. So the first result is that the temperatures, despite the optimal and suboptimal periods that we were preconceiving because of the fluctuations of the oceanic oscillations, the temperatures still kept increasing. And these are the temperatures in spring, and these are the temperatures in summer. So the temperatures in spring were increasing. You can see from suboptimal to optimal in the last 10 years is basically going on. And it is more temperature increments in the most sheltered or protected areas than in the least protected or more exposed areas. About the frequency of marine heat waves, we had more frequency of heat waves in the suboptimal years. So the years in which the PDO and ONI were positive, we had more intensity of marine heat waves. This plot is showing the temporality of these heat waves. This is taking into consideration 40 years of data. And in 40 years, we had an average, percentile, and 90% percentile, and then all the days that went beyond that level for that time of the year is considered as a marine heat wave for more than 5 days. So you can see that there was a lot of concentration of marine heat waves in the optimal years. And this is using as data the SST records of the lighthouses. There are 3 lighthouses in the Salish Sea that we are using as a reference. And in wind, we had more frequency of extreme events in the optimal periods. So these plots are showing the maximum wind beyond 2 standard deviations using the average. And in the optimal periods, we had more frequency of extreme winds in in the southern part in summer months, and in the optimal 2, we had more increments of wind in Hollywood Bank, which is a place located in the center of the Strait of Georgia. So what about kelp? So these plots are showing the distribution of the kelp we mapped using all of the coverage for all the time, and with that we had a total full coverage called the kelp niche per segment, per cluster. And we saw what was the fluctuation of the kelp into this kelp niche. So in general, the kelp cover fluctuated between 0 to 50% of the total kelp niche per every period. But, okay. And this is the suboptimal 2 period, which is also called the blob. And our question was, what was the main difference of the blob compared to previous periods? So we took the previous period, the optimal 1, as a reference, and then we mapped what was the difference in space or in coverage after that. What we observed is that the clusters didn't change that much, or didn't change in a decreasing way. They stayed within the reference bounds. The reference bounds are here in this gray band. So the average and standard deviation of all the kelp per cluster was within or even above the reference record. We observed that cluster 3, the reference is going down of the reference, and clusters 2 and 4 are increasing a bit more related to the reference years, but they are not exactly like decreasing dramatically. They are staying more or less into a plateau of temporality. And using the data of Ella Beach, located here in Zug, in this little star, and mapping all the kelp coverage, we can see that there was no trend, but also there was no trend in the temperatures. The temperatures over the last years are more or less stable in this area of Juan de Fuca in spring and summer. So despite the PTO and ONI, the local conditions around Ella Beach are quite stable, and so that's the kelp. So in conclusion, kelp shows a general resilience, in overall resilience, but for different reasons. So the coldest and the most exposed area, cluster 1, Juan de Fuca, have the best conditions for kelp. The temperatures have increased, but not that much. They are within the range of less than 16 degrees Celsius in summer. So there are still like good temperatures for kelp to grow and reproduce. And they are also exposed to high winds in summertime. The warmer and more sheltered areas might have benefited by wind and wave forcing, because as you saw, there was more wind in the summer season and in the winter times in the Strait of Georgia. So we wondered that maybe that was an effect that accelerated the dispersal, the connectivity, and maybe the growth of the sporophytes. And in the warmest areas of the Strait of Georgia, so in the cluster 3, looking at the Strait of Georgia, are moderately resilient, and they will probably need more attention. They are doing fine, but maybe are less resilient than the other areas. So I think that was it. I see that I'm going just in time, so.
Yes, thank you so much. Really fascinating project, and congratulations on your recent publication. If folks have questions, we have time for 1 or 2 before we wrap up. You can raise your hand or put them in the chat. And I think there is a number of questions or comments that came in, but maybe they're answering prior questions. Let's see. All right, folks, feel free to raise your hands if you have any questions.
I can't find my little hand, so I'm going to use my real hand. And apologize for that other. But Alejandra, I'm really interested, and I'm wondering, because during that period, we did see complete loss of floating kelp beds in some parts of Puget Sound, especially the warmer parts. And you're saying, and I think about the area you looked at as a real comparison. And of course, Strait of Georgia can get warmer. So, you know, what we saw was Strait of Juan de Fuca remained very resilient and stable. And then we saw complete loss. But the beds that were lost are smaller. So from an aerial perspective, they don't count. But they do count from a frequency perspective and a geographic extent perspective. Did you not see loss of beds in some of the warmer regions? So is that result different from ours in the 2014 to 2018 period?
Yeah, so thank you for this question, because this is what we actually observed, but in other areas of the Strait of Georgia, so in the northern part of the Strait of Georgia, we see that there is some total loss, complete loss. And this is also correlated with the warming trend of the Strait of Georgia that is super similar to what you observe in Puget Sound. So I think that in that area, in that specific area that we are looking at, which is southern part of the southern Gulf Islands, we see that moderate resilience to the warmer temperatures because of the nutrients that are flowing through the plume of sediments of the Fraser River that are smashing that coastline with tons of nutrients. And I think that will make a buffer for the sporophytes to survive and keep doing their lives despite the heat. But I don't know if it's going to last for longer. At least they're doing fine, but yeah, we don't know about the future. But in the northern parts, so the central and the northern part of the Strait of Georgia, this is something that we are actually seeing, and we will publish about this soon. The paper is on the oven now, in the oven.
Great. Well, thank you so much. We look forward to hearing more about that in coming meetings. And thanks to all of our presenters today, giving a virtual a round of applause to everyone who's attended. I personally am really struck with the variety of methods that we're tackling, understanding what's going on with the kelp community through drones, aerial images, kayaking, snorkeling. I think that today really captured the breadth of ways that we're kind of digging in and trying to understand what's going on. So thanks to you all for the fantastic work you're doing and continuing to show up and share. We are going to wrap it up here. And so folks can leave if you want. I'm going to keep this open though, if folks want to ask continued questions or have other questions you want to ask any of the presenters. So if anyone wants to hang around, I'll keep it open, but also respecting that it's people might have other meetings they need to hop off onto. So thanks again to everyone who attended today and presented. Bye.
Thank you. Bye.
Thanks, everyone.
Perhaps we can just wrap it up, Bree, by saying next meeting in October. And we would love to hear from anyone who has anything to share. It's wonderful that you all are so willing, and it's great to see your work.
Yeah. Helen, you really packed it in today.
Oh, and you know what? October's going to be great. I promise you. And we're already stacking up presentations. So stay tuned. And thank you so much to everyone. And we'll see you on Zoom, and hopefully we'll see you all in the field. Let's all get outside together.